Alright, hello everyone. Hopefully I'm not too loud. I haven't done this in a while, and I'm doing this on a new system. So, yeah, welcome to the stream. We're going to go over the Exam 1 practice exam, which it explicitly said not to study, but we're going to go ahead and study it anyway. Whoops. Okay, so here's what we're going to start with. Okay, number 1 is asking the property that distinguishes an atom of one element, carbon for example, from an atom of another element, oxygen for example, is A, how many bonds it forms, B, the number of protons, C, the number of neutrons, or D, the type of element that it could bond with. Okay, so let's work down the chain, right? So just as a start, we have 3 types of subatomic particles, right? And I like to make this one red, this one gray, and this one yellow, right? So this is a proton, right? So proton has a positive charge. And this is a neutron, and neutron has no charge, so it's equal, right? I put an equal sign here. And this is an electron, which has a negative charge, right? So these are your subatomic particles. So you take all of these, you mash them together, and boom, you get an atom, right? So, for example, a atom of hydrogen will have 1 proton, and surrounding it is 1 electron. And an atom of helium will have 2 protons, because it's next in the periodic table. 2 protons, 2 neutrons. Sorry. And 2 electrons, right? So as we keep on going, for an atom to stay electronically neutral, it has to have the same amount of protons as it does electrons, right? Once we start changing the number of electrons, then we start to get into ions. And once we start changing the number of neutrons, we start getting into isotopes, right? So let's say for this hydrogen atom, for example, for this hydrogen atom, what if we add a neutron? Okay, so now it's hydrogen 2. Otherwise known as deuterium. Okay, so what if we add a third one? So now this is hydrogen 3, also known as tritium, right? So isotopes, right? Okay, so here's what each of the particles do, right? So electrons pretty much solely have to do with the reactivity, right? So especially electrons on the outermost shell, and we call that the valence shell. So we call that the valence shell. So electrons are very reactive. That's what causes all the chemical reactions. It's just the shifting around of electrons and the creation of bonds, right? So that's what an electron does. What a neutron does is it just balances out the weight, and it balances out the charge within the nucleus, right? So look at this helium atom over here, right? So this is helium, right? So what does helium do? Helium has 2 protons, right? But as you guys know, with playing around with magnets, right, is that opposites attract, and things that are similar repel each other. So how is it that protons can stay together like this, right? How is that possible? Well, it's through neutrons, and it's through something called strong nuclear force, right? So the neutrons help balance out the protons so that the atom can actually stay together, right? So that's why helium is so stable, right? Because we only have the 2 protons and we have the 2 electrons, and the electrons on the outer shell they do not want to be donated. They do not want to accept anything. Nothing is happening to these electrons because this is a full valence shell, right? So once we get into the other valence shells, there's only 1 valence shell, right? So once we start getting into other shells, then it goes up to like 8 per shell. But for the innermost shell, it's 2, right? So it's 2, then 8, 8, 8, 8, and then if you take chemistry, it's like it gets weird, right? There's always an exception to the rule, right? Things are not always so neat. However, right, that's the purpose of the neutron and of the electron. So what does the proton do? Right, we've been talking all this time. What does the proton do? Well, the proton determines the element itself, right? So let me pull up the periodic table real quick. Just give me one moment. So my favorite periodic table resource is just ptable.com. So that's where this is from, right? So this is your periodic table. So let's look at what we have here. So we have hydrogen. So we have hydrogen, and then it goes all the way to helium, and then lithium, beryllium, boron, carbon, and then just goes down the chain, just down the chain, right? So that's what that does, right? We just go down, right? So 1, 2, 3, 4, 5, 6. Okay, and these so this number up here, these numbers represent how many protons there are in the atom. That's the atomic number. So the atomic number, right? The atomic number is the same as the number of protons. Write that down. The atomic number is the same as the number of protons, because you will most likely get a question like that on the exam, right? So that's what it is, the atomic number. So we have a few things here that we need to worry about. The atomic number, the symbol, the name, and the weight, right? So the atomic number tells us the number of protons. It tells us the properties of the element, right? The symbol tells us the 1 or 2 letter abbreviation of the element name. The name is, of course, the name of the element. And the weight is the average of every single atom in the universe of that element, right? The average weight, right? So we talked about isotopes, right? So let's take carbon, for example. Where's carbon? We take carbon, for example, right? So carbon always has 6 protons, right? But sometimes, so carbon has 6 protons, right? And it's going to have 6 neutrons. But sometimes it has sometimes it has 7 neutrons. And sometimes it has 8 neutrons, right? So what we do is we take the average of all carbon atoms. We like take a sample and we annihilate it, and we detect what it's consisting of, right? And when we add up the number of neutrons and protons, we get the atomic mass, right? And the atomic mass is just the mass of one atom. When we talk about the atomic weight is the average of every single atom in the universe of that element, right? So carbon-12 has 12.01, rounding up, right? 12.01. Nitrogen has 14.001, or 14.01, rounding up again. Oxygen, 16, right? So we just take the average, right? Because sometimes there's going to be a nitrogen with 8 neutrons, or sometimes there's going to be an oxygen with 7 neutrons, that sort of thing, right? So I can't confirm if you guys like actually understand this. So, but yes, I would if I could. However, that's what the atomic weight is. The atomic weight is an average. The atomic mass is a specific calculation of one atom, right? So right, if we're taking like helium, right? If we're taking helium, for example, so we're just talking about helium. So helium has 2 protons, and 2 neutrons. So essentially what we just do is we just add this, and we get an atomic mass of 4 AMU. AMU is atomic mass unit, right? Which I'm not sure if you need to know this for the exam. We'll go into it later. So I'm sure some of you may be asking, what about electrons, right? So electrons are so small. Imagine how tiny a proton is, right? An electron is 0.008% of the mass of a proton. Does that make sense, right? I might wait. Okay, one. Okay, sorry. Yeah. Okay, so the mass of an electron is 1.008% of the mass of a proton. Yeah, 1.008, which is tiny, 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 tiny. So electrons, unless there's like a lot of them, they which even then it would barely consider, the weight would still barely be considered. It's almost negligible. But these electrons still have a little bit of mass, just a little bit, right? But it's just a fraction of a percent, a fraction of a fraction, however you want to say it. It's so much smaller than that of a proton and of a neutron that we don't consider it in the mass calculation of an atom, right? So don't even worry about electrons when it comes to that. However, right, it's so small, then why do they have why do protons and electrons have the same charge? That is a question I cannot answer. You'll have to ask like a theoretical physicist or whatever. But yeah, one thing I do want to emphasize is that protons and electrons have the same charge. They have the same amount of charge. Just one is positive and one is negative. And that's going to be very important later on when we talk about reactivity and ions and like attractions and whatnot. Yeah, but they have the same charge. But one's positive, one's negative, right? So anyway, that was our discussion about the subatomic particles, right? One accounts for reactivity, and that's the electrons, right? One accounts for stability, and that's neutrons, and one accounts for the properties of the element, and that's protons, right? So yeah, that's the basics of the atom. The atom is what makes up everything in the universe. Everything that has mass is going to be made up of atoms. And of course, there are things that scientists theorize about, like dark matter or dark energy. But anything that has mass is going to be made of atoms, right? So anyway, lengthy explanation over. Let's go back to the question, right? So the question is asking, what distinguishes one element from another? How many bonds it forms, the number of protons, the number of neutrons, or the type of element that it can bond with. Okay, so let's go down the line, right? A, how many bonds it forms? Well, okay, how many bonds it forms? Well, carbon can form... wait, I just want to... Okay, yeah, okay. Carbon can form 4 bonds, right? Well, one's just one space down, one column in the same column, one space down. Silicon can also form four bonds, right? So that is not what distinguishes these from each other, right? Just the number of bonds that could be formed. I mean, of course, you have hydrogen. Hydrogen can form 1, and you have oxygen. Oxygen can form 2. Sure, those are different, but that's not what accounts for what makes them intrinsically different. The amount of bonds they can form, well, like I said, carbon and silicon, they can form the same amount, right? Oxygen and sulfur, they can form the same amount. Chlorine and bromine, same amount. Again, right? That's not what differentiates them. So how about the number of neutrons? Well, we just went over, right? The number of neutrons is how you distinguish isotopes, right? So that's elements of the same kind, of the same amount of protons, which, yeah, spoiler, right? But the number of neutrons determines the difference of isotope, but not the difference of element, right? So yeah, you could have a hydrogen atom with two neutrons, and you could have a helium atom with 2 neutrons. That's not what makes them different, right? So how about D, the type of element that I could bond with? Well, all sorts of elements can bond with all sorts of other elements. Hydrogen can bond to oxygen. Oxygen can bond to carbon. Silicon can bond to carbon, or probably. Anyway, that's not all what distinguishes it. So A, C, and D are all wrong. But how about the number of protons, right? Like I said, atomic number, right? Atomic number is the number of protons, right? So let's see if I have it. Yeah, here we go. Atomic number is the number of protons. So that's what makes each one of these different, because some of these can have the same amount of electrons. Some of these can have the same amount of neutrons. But all of them have different protons, because if we change the number of protons, we are intrinsically changing the element, right? So this is why scientists, this is why what are they called? Alchemists, right? This is why alchemists would try to turn lead, over here into gold, right? So what happens if we take away, oh, and they didn't know this, of course, because this is really difficult to do. It is possible, but it's really, really difficult and very expensive. So if we subtract 3 protons, bam, we get gold, right? Easy trick to get gold, except it's really not, right? That's what alchemists were trying to do for so many years, is that they were trying to intrinsically change the elements in which they were dealing with. If we change the proton, we could do exactly that, right? If we could change the number of electrons, still the same element. We change the number of neutrons, still the same element. If we change the number of protons, that's what differentiates carbon from oxygen, or oxygen from hydrogen, or hydrogen from silicon, or silicon from helium. All of those, right? So that's question number 1. Yeah, that was a very lengthy explanation for just one question. That was 16 minutes of explanation for one question. So I'm gonna try and speed it up a little. Yeah, hopefully the rest of these questions won't take as long. I'm trying to be comprehensive as we go along, right? Because I'm sure a lot of you have a lot of questions, right? All right, so next question. I have a lot of trouble with this. I don't know why. There we go. Okay, so question 2 is asking. Okay, there's a typo. All right, there's a typo. Oh, okay, well let's just fix it. Sorry, please bear with me. An atom. That's what it's supposed to read. An atom. Okay, an atom with a net positive charge must have A, more protons than neutrons, B, more protons than electrons, C, more electrons than neutrons, or D, more electrons than protons. Okay, so we can just go ahead and eliminate C, right? Because remember, neutrons don't have any charge, so we could just go ahead and get that out of the equation. And we do the same with A, right? More protons than neutrons. Once again, neutrons have nothing to do with charge. So, an atom with a net positive charge. So my question is, right, if we have a lithium atom, so lithium has an atomic number of 3. If we have a lithium atom, and that has the inner shell of 2, right, and then the valence shell. So remember again the valence shell. The valence shell is the one that's going to be reacting. So if we have lithium, we have the nucleus, and we have the inner shell, which holds 2, and then we have the valence shell that could hold 8, right? Well, for now, we have 3 protons and we have 3 electrons. So 3 positive and 3 negative. What happens if we add this, right? Or well, let's there we go. 3 positive plus 3 negative. What happens if we add that? 0, right? Of course. So what happens if we take away what happens if we take away an electron, right? If we say goodbye to that electron. So now we have more protons than we do electrons, right? So let's count them, right? So we have 3 protons, right? And then we're adding 2 electrons, which have a negative charge. So we have a positive charge, right? That's positive. So we indicate this atom to have a positive charge. So we would say this is lithium normally. We would now say this is lithium with a positive charge, kind of looking like this, right? So, yeah, let's go back to the question. If we're losing electrons, we're gaining positivity, right? Because electrons are negative. And if we're gaining electrons, we're getting more negative, because once again, you're adding negativity, right? So an atom with a net positive charge must have more protons than it does electrons. So the answer is B. So moving on, number 3. So we talked about isotopes, right? That's the name of our baseball team, right? Or in New Mexico. The isotopes. Who doesn't love a good isotopes game? I haven't been to one since I was very young. If this will work, please. Oh, there we go. That's what I should do. Okay. So number 3 is talking about isotopes. So the isotopes carbon-12 and carbon-14 differ in the number of neutrons, the number of protons, or the number of electrons, or D, B, and C. So remember what we talked about? How if you change the number of protons, you change the element. So we could just go ahead and eliminate B, and by extension, D, right? So process of elimination, right? So carbon-12 and carbon-14, right? So what do these numbers mean? What do these numbers mean, right? These numbers tell us the atomic mass, right? So when we're talking about atomic weight is an average. Atomic mass is a calculation of one atom, right? So carbon-12, that's going to be 6 protons, because remember the protons don't change. Carbon has 6 protons plus 6 neutrons. Or how about this, right? We have 12 equals 6 plus x, right? So find x, right? And you balance out the equation, x equals 6, and that's our number of neutrons, right? So when we add 6 plus 6, we get 12, carbon-12. 6 protons, 6 neutrons. And remember, we do not include electrons in this calculation because electrons are tiny, 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 tiny little things. So how about carbon-14? 14 equals 6 plus x. Well, what does x equal now? 8. So this will have 8 neutrons, right? So that's just basically how you calculate the number of neutrons if you don't have it, which if you will always have the number of protons, right? Because once again, you need the element, when the element doesn't change the number of protons, right? If it's the same element. And if we're trying to do this in reverse, if we're trying to do this in reverse, 6 plus 8 equals 14, carbon-14, that sort of thing, right? So that's how you calculate the atomic mass, right? You just take the number of protons plus the number of neutrons, right? So not the number of electrons, right? That's not how these differ. So we could go ahead and eliminate that, leaving A as the correct answer. All right, moving on. Okay, so number 4 is asking about the most commonly found the most commonly found elements in organisms, right? So for this, you have to know what these most commonly found elements are. So what are they, right? There's 4 that you have to know. There's 4 that you have to know absolutely, right? Because these are going to show up for the next 4 months of this class. You absolutely have to know these. Hydrogen, carbon, oxygen, and nitrogen. So hydrogen, carbon, oxygen, and nitrogen. So these are the 4 most common elements in the human body, and in most living things, and in all living things, actually. Sorry, I misspoke. All living things have these 4 elements in common: hydrogen, carbon, oxygen, and nitrogen. You take these 4 elements with a few others, and you're able to make life. That's why life is so hard to find, because sometimes you can't find liquid water, or carbon is not available. Whatever, right? So it's just really humbling, right, how we are even alive, honestly, and how we were able to. Okay, I'm getting too philosophical. Let's just move on. So let's analyze these four important and necessary elements. Let's analyze them, right? That is tiny. Okay, there we go. So where are they? We have hydrogen over here. We have carbon, nitrogen, and oxygen all over here. They're even in a row. How nice, right? So we don't worry about boron. We don't worry about beryllium. We don't worry about lithium. Even though we just went over lithium, right? These are not organic. These are not found in organisms, and not helium either. As fun as helium is. So what do these have in common? So let's go down the list, right? A is saying they all have a low atomic mass. Okay, well, I guess you can say that. I mean, compared to some of these other elements, yeah, they are very low. I mean, look at radon gas. It has an atomic mass of 222. That's a lot, right? So we could say that is a property of elements found in organisms, right? It has a low atomic mass. Well, how about elements have an atomic number less than 21? Well, that's also true, because where's 21? Scandium, right? Well, we have 1, 6, 7, and 8. I don't know about you guys, but that's less than 21, right? So how about C? The elements all possess 8 electrons in their outer shell. Ooh. The only elements that possess 8 electrons in their outer shell, by default, are these ones on this side. These are known as noble gases. Noble gases are stable. They do not want to gain or lose any electrons because they're already set, right? But hydrogen can form a bond. Hydrogen has 1 valence electron. Carbon can form 4 bonds. It has 4 valence electrons. Nitrogen can form 3 bonds. It has 5 valence electrons. And oxygen can form 2 because it has 6 valence electrons. Right? It still has these spots that are waiting to be occupied. Right? So this one is false. How about the elements are lacking 1 or more electrons from their outer shell? We just talked about that. That is true. So the answer is C. This one is not a property of elements. This is not a property of elements most commonly found. Right? So for this question, you have to know what the elements are. Like I said, you have to know these 4. You have to know them. Please. Please, please, please. Anyway, moving on. Whoops. Alright, so now we're actually talking about bonds. Specifically, now we're talking about ionic bonds. So there are 3 types, well, technically 2 types, well, 2.5 types, let's say that. There are a few different ways elements can interact with each other, right? So we still need to talk about bonds, so now we're going to do that, right? So there's a couple of different ways this can happen. Through the sharing of an electron or through the exchange of an electron. So, when we share electrons, okay, how about that? Sorry, 1 second. When we share electrons, sorry, I have a new keyboard, it's kind of throwing me off. When we share electrons, that is known as a covalent bond. No, covalent dong. That's funny. Covalent bond. That is when we share electrons. How about when we exchange electrons? That is an ionic bond. So yeah, so there are two, and furthermore, there are two types of covalent bonds. When we share unequally, and when we share equally. And when we share them unequally, this is known as a polar covalent bond. And when we share them equally, these are known as non-polar covalent bonds. So yeah, these are your three types, right? Polar covalent, non-polar covalent, and ionic. So yeah, going back to the example. Okay, let's start. Let's have a new example, right? Let's go to sodium, right? So sodium's atomic symbol is Na. So why it's not like SO is because Na is like, it's like natrium, and natrium, the sodium was discovered like in ancient Rome, and they were speaking Latin. Whatever, doesn't matter. So sodium has an atomic symbol of Na, right? Sodium has an atomic number of 11, right? So how many valence electrons does it have, right? So let's take 11 minus 8 minus 2, right? Because remember, there's two, because electrons, they come in shells, right? So in the innermost shell is 2, and beyond that it's 8, right? So let's okay, real quick, let's explain why that's the case, because I could see why that would be confusing, right? Okay, so hydrogen and helium have, so on the innermost shell that's 2, right? So bam, 1, 2, and then we move down, 1, 2, 3, 4, 5, 6, 7, 8, and then we move down, 1, 2, 3, 4, 5, 6, 7, 8, right? So helium has 2, right? It has 2 valence electrons, so it's perfectly even. Neon has 8, right? So 10 minus 2 equals 8, right? And then argon 18 minus 8 minus 2, 8, right? So we just go whoop, and then we go this way, and then we go this way, right? So elements in this column are going to have 1 valence electron. Elements in this column are going to have 2. And then we jump over, because we forget about the transition metals. We jump over, these ones have 3, these ones have 4, these ones have 5, 6, 7, and then 8, right? So that's how we calculate the number of valence electrons, right? But once again, the only ones that you really need to know how many there are and how many bonds they can form are carbon, nitrogen, oxygen, hydrogen, right? But in the case of ionic bonds, which we're talking about now, we have to focus on these ones over here, right, and these ones over here, most likely, right? So anyway, so sodium, we calculate the number of valence electrons by taking the atomic number, which is 11, right, subtracting it by 8, and then subtracting it by 2, right? So then we get 1. Right, so 1 valence electron. So I would draw in all the protons and all the neutrons and all the electrons. I'm just gonna go ahead and shorthand it because that's a lot easier for me. So what I mean by shorthanding, I'm drawing the elemental symbol, Na, and then 1 valence electron because that's how many it has. I'm ignoring everything else inside, right? So that's just how you shorthand it. You just do the valence shell and the name, right? So this is sodium. Sodium is very reactive. I mean, look up on YouTube, like throwing sodium into a pond of water, right? It explodes. It goes all over the place. It catches on fire. Like I said, super reactive, right? Because sodium is dying to get rid of this valence electron. It is dying. Needs to get rid of it because it wants to be stable. It wants to have 10 electrons, so it fills out the 8 and the 2. It just wants to get rid of that one. That's why it's so reactive. So what happens to this electron now? Well, that's where chlorine comes into play. Right? It doesn't have to be chlorine. It could be iodine, or it could be bromine, and there are other ionic bonds that could be formed, right? But sodium and chlorine go together like peanut butter and jelly, right? These two just love to be together. Who doesn't love a nice little salty meal or salty bag of chips, right? That's where this comes from, right? So we have sodium and we have chlorine. Chlorine has an atomic number of 17, right? So that's 17 minus 8 minus 2 gives us 7, right? So chlorine has 7 valence electrons. There we go, 7. Which I had a question about this the other day. When we're counting valence electrons, let's use let's use nitrogen as an example. Let's do it in blue. I think nitrogen is like a blue element, if that makes sense. In my mind, it is. If we draw the valence shell, right? We go 1, 2, 3, 4, and then we go back up top, 5. And there was one more, we would go down here again, right? So we fill them out individually first, and then we start adding them in pairs. That was one question that I had the other day. So anyway, sodium and chlorine. So remember how I said how reactive sodium metal is? Chlorine is the exact same thing, right? Chlorine is dying to fill out that 8 shell, that shell of 8. It's just dying to get 18 electrons. Well, these two can solve each other's problems, right? Sodium can go ahead and just donate its 1 electron to chlorine, and chlorine can accept that 1 electron, making a full shell for both of them. So in this process of losing this electron and giving it to chlorine, this process of losing and gaining, right? So let's just cross it out because, yeah, whatever. So in this process of loss and gain, sodium now has a positive charge because we fully lost an electron, and chlorine has a negative charge because it gained negativity. So do you remember what I said about opposites attracting? Bam! That's what happens. Opposites attract, and what happens to these is that if we have a lot of sodium ions, because remember, these are now ions, because we have a different number of electrons than we started with. That's an ion. That's what an ion is, when we have a different number of electrons than we do protons. When we have ions, they kind of create a sort of lattice when we have a bunch of them. So let me show you. Just give me one moment. Right, so if you ever look at like salt underneath a microscope, right, you will see that it has like this sort of crystalline structure. It's like cubic, right? It's very it orients itself in like a cubic formation. That's what's going on here. That's if you look at a molecular level, or at a atomic level rather. If we look at an atomic level, we can see how these ions are orienting themselves in space, right? So we have these purple sodium ions and these light blue chlorides, right? So these are they're just attracted to each other, and through this they create a bond, and this is an ionic bond, because they're both ions, right? So the electrostatic interaction between them keeps them together, and that is its own compound now. So chlorine no longer has the properties of regular chlorine. It has the properties of a chlorine ion. And same thing with sodium. Sodium is no longer a highly reactive metal. Sodium now tastes good, right? It tastes delicious, right? That's why we love salt. Salt is awesome, right? So that's what's happening here. If you licked sodium metal, it would not end well. But if you lick like a rock of salt, tastes delicious, right? And this is why, because the properties of the element changed because we changed the number of electrons, right? So that's an ionic bond. So once again, super long explanation for one question. So ionic bonds arise from not shared valence electrons, because remember this sort of flow chart that we have going on here. It's through an exchange, right? So not shared attractions between neutrons. Well, once again, neutrons cannot attract anything because neutrons are neutral, right? Attractions between ions of opposite charge. Okay, we're getting somewhere. An attraction between neutrons and protons. Once again, drop the ball. Not neutrons. It can't be neutrons. Neutrons do not attract anything. So attraction between ions of opposite charge. That is what an ionic bond is. Ions of opposite charge, they like to hang out together now. Right? That's what it is. It's as simple as that. Right? Yeah. So, moving on. Well, let's... okay, so while we're on the topic, right? While we're on the topic, let's go over covalent bonds, right? So let's just go ahead and delete this question, right? Because we're no longer talking about it. Let's take this little thing, right? So we were just talking about the full exchange of electrons, and that's an ionic bond. So what about a covalent bond? What is a covalent bond? What does it mean to share electrons? Right? Well, let's find out. Let's take hydrogen. Hydrogen is the most simple example of this, right? Hydrogen has just one valence electron. Just the one, right? So if we take another hydrogen atom, it has also just the one, right? Yes. Okay. So these two want something to happen to that electron. So hydrogen has a couple of different options. Either it can donate its electron. That is possible. We will go into that later in the semester. Or it could share it. Most times it'll share it. In certain cases it won't. But hydrogen hydrogen is very versatile. So in this case, when we're bonding hydrogens together, right? When we're bonding these hydrogens together, what is going to happen between them, right? Because they both need two, but it's not exactly favorable for one to donate and one to accept. So what happens now? What happens is they share. Bam, they share. That's exactly how it happens, right? So let's draw it like this, right? So we have one hydrogen atom with one electron here, right? And then we have another hydrogen atom with one on the other side. So what's gonna happen now? They are going to be shared just like this. Bam. Oh, well, that's kind of misleading. Let me think about this for a second. Okay. Okay, nope, this is wrong. Okay, I know now. I got it. So you guys are gonna have to bear with me. So these two, they come together, and there we go. They come together, and now Sorry, that's still like kind of okay. Let's get them as close as we can. Right. Bam. Okay. Touchdown. Right. So we've gotten them as close as we can. Right. So when they get close together like this, now they could actually share electrons. Right. So this one can like essentially just make a bridge, and this other one that we kind of erased can also make a bridge. And that's a covalent bond. They're sharing, right? Isn't that beautiful? Don't we just love sharing, right? Some of you maybe not. I hope that's none of you, but some of you maybe. Hydrogen atoms love to share. Carbon atoms love to share. All these elements love to share electrons, right? Hydrogen specifically can only share one. So hydrogen is sharing one with another hydrogen, and that same hydrogen and that other hydrogen is sharing one with the other one. So they have now completed each other's shells, which is great because now they're both happy. So now we call this hydrogen 2 with a little subscript 2, right? Hydrogen gas. That's what this is. Hydrogen gas. So when you light hydrogen gas on fire, because this is highly flammable, when you light hydrogen gas on fire, we just get water. Okay, so when we add oxygen to the mix, yeah, we just get water and some heat, right? That's a chemical reaction. You don't need to worry about that for now. In fact, I don't even know why I'm going over it, if I'm being honest. Okay, so that's just a covalent bond. Is when two atoms like to share their electrons, so they fulfill each other's needs, right? Making an entirely new compound, and making an entirely new compound or element, right? Just through the sharing of electrons, right? So, as kids, right, sometimes you would get into arguments with your friends or your siblings about sharing things, right? So let's talk about water now, right? So hydrogen and hydrogen, they have the same strength because they're the same element, right? They share these electrons equally. So remember, going back to the flow chart, when we share equally, that is a non-polar covalent bond. So they're sharing them equally. There are no poles, and we'll go into what that means later. There are no poles. There is no positive or negative charge. This is neutral. It's non-polar. There is no like charge associated with this compound, right? But like I said, let's move on to water. So water, right, is H2O. So what does that mean? You've heard that your entire life, probably. Water is H2O. It's probably the only chemistry-related thing that you knew for years and years of your life. But what does it even mean, right? So oxygen has a valence shell. It has 6 valence electrons, right? So remember, we count 1, 2, 3, 4, right? And then 5, 6. So yeah, so we have 2 unoccupied spaces in which we could bond. 2 electrons that are willing to share, because these are known as lone pairs. These are LP lone pairs. These are lone pairs because there's nothing you could do with them, right? They're happy as they are. They exist in their own little space, right? Because we want these electrons to be paired, right? That's ultimately the goal. We want these electrons to be paired, right? So of course, in hydrogen, in the example of hydrogen, you're already looking for one pair, right? But when we get to the outer shells, like 8 and 8 and 8, right? When we get to the outer shells, then we start to discuss these lone pairs. So we want these electrons to be in pairs, right? So there's one pair that can be made here, and one pair that can be made here. So let's take hydrogen again, right? So hydrogen has just the one electron, and hydrogen has already gone ahead and bonded to oxygen. Okay, and we do that again with another hydrogen, because once again there are two opportunities for sharing here, right? Just like it did with just like hydrogen did with itself, we do here with oxygen, right? So bam, just like that. So now we have a water molecule. This is a water molecule, H2O. Good old water. Couldn't live without it, literally. So now everyone's happy here. Hydrogen filled out its one valence electron. It filled out that pair. Both of these did, right? And oxygen has a full shell of 8 now, because now we're sharing, right? However, oxygen is a little bit greedy. So this is where we get into the discussion of electronegativity. Electronegativity. Right, so electronegativity, every single element has its own electronegativity value. Hydrogen has like an intermediate amount. Oxygen has a very high amount. So what the heck does the electronegativity even mean? Electronegativity means the affinity for an element to pull electrons towards itself. Did you get that? Electronegativity means an element's affinity to pull electrons towards itself. What a mouthful, right? Electronegativity in itself is also a mouthful, right? But what it's essentially saying here is that oxygen, like I said, has a high electronegativity. Hydrogen has like medium, right? So essentially what's going to happen is that these electrons are actually going to be pulled closer to oxygen than they are to hydrogen, right? So if you had a kid, if you knew someone that was a little bit greedy with their toys, right? They'd like to hold on to them a little closer, but you're just still trying to share, so you grab out your arms, right? That's what oxygen is doing, right? Here hydrogen bonded to hydrogen, H2. They're happy. They're happy together. They share equally. Here with water, they share unequally, right? Oxygen is a bit of an electron hog, right? Because of its high electronegativity. So here I've drawn what's known as a dipole. Dipole essentially just shows, it's essentially a vector of where the electron's charge is going, right? It's a vector of where the electron's charge is going. So if the charge is going towards oxygen, as we see here. So if we add vectors together, so essentially, bam, it's just kind of like that, right? So that's what's going on here, right? So in this process, in oxygen hogging all of its electrons together, right? We then create a partial. Okay, so this is a lowercase delta. This is partial. This means partial, right? We create a partial positive charge here in one hydrogen, a partial positive charge here in the other one, a partial negative charge on the opposite side, and then another one here. Bam. That's water. Water is the only molecule, as small as it is the only molecule that can have 4 different spots that are partially charged like this. And this is what when we say something is polar, this is what we mean. So you think of the North Pole, you think of the South Pole, you think of the magnetic poles, right? You have a magnet, let's say, you have a magnet. So who loved playing with magnets as a kid? I love magnets. So we have one side, we have one end that's heading north, and we have the other side that's heading south, right? North and south. In the same sense, so those are magnetic poles. In the same sense, we could say that about this molecule, right? With the polar covalent bonds, we could say that about this molecule. One pole is positive and one is negative. It's as simple as that, really. It's just like a magnet. One side is positive, the other one is negative, right? So if we take this, right, and we like I don't know how to rotate this. I'm gonna be honest with you guys. And so this side, oh, it's going to be attracted to the partial negative, and this side, oh, it's going to be attracted to the partial positive, right? Because remember, opposites attract. Guys, this is, it's all, you guys have to tap into your logic. You have to tap into things that you learned as kids. You have to tap into like everything that you know, because this is what we're made of. This is what we're made of, and we're learning about what we're made of. Isn't that such a beautiful thing that we're learning this? We're able to understand this. Guys, I'm telling you, this is so important. The fact that water is able to do this is magical. It is almost, I mean, we have the logic right here. We could study it. We could look at it. But guys, I'm telling you, this is magical. The fact that water is partially positive on one side and partially negative on the other. And that has an entire slew of different things that it could do with that, right? Which is why we're going to go into hydrogen bonding next, right? So let's delete this magnet. We love magnets, right? Like I said. Sorry, one sec. Okay. So let's go ahead and erase some of this. You have to bear with me. This software that I'm using, some of you may recognize it. It's not the greatest in the world. It is free, and I am used to it, however, so, you know, you work with what you got, right? And let's go ahead and fill in these dipoles too. Why not? Or let's just go ahead and erase them. Okay, that didn't do what I wanted. You guys are just watching me struggle at this point. You'll have to bear with me. Okay, so we just talked about polar covalent bonds, right? How one side is partially positive and the other side is partially negative, right? And that has to do with the pole, the electron affinity for oxygen. Oxygen pulling the electrons towards itself from hydrogen, right? Making itself more negative and making the hydrogens more positive. So what do we do with that? Well, what happens if we go ahead and add, bam, another oxygen? Sorry, another water molecule. Do you remember what I said about opposites attracting? Well, once again, that is coming into play, right? Because what's happening here? Let's add in some partial charges so we can see what's going on. Hydrogen has a partial positive charge, right? And this lone pair, or this side of water, has a partial negative charge. So what's going to happen here? Hydrogen bonding. That's what it's called. Hydrogen bonding. So what we discussed over here, this is what's known as intramolecular forces. Intramolecular forces. Hydrogen bonding is an example of intermolecular forces. Intra meaning within, inter meaning between. Right? So ionic bonds and covalent bonds, those are intramolecular forces. So when we're talking about inter, so intra, that has to do with the bonds within a molecule, right? So these polar covalent bonds, that's within the molecule, right? So good. Inter is between other molecules. So we have one water molecule here and one here, right? These couldn't form a hydrogen bond without each other, right? They need each other to form a hydrogen bond, which is why it's between two molecules, right? But back to the topic, right? Right here, we have a partial positive charge and a partial negative charge. What is going to happen with these, right? What's going to happen with these is that they are going to attract to each other. Which, like I said, magical. Water is incredible for its ability to do this. And they could do it with 4 other spots on the hydrogen molecule. Like literally, if we take multiple of these, they just create this lattice. They create this beautiful structure of just water interacting with each other, like an entire like ecosystem essentially of just water, right? Through sheer electrostatic interactions like hydrogen bonding. These are attracting to each other. One is positive, one is negative. Bam, they come together. Just like that. However, it's not like an ionic bond where they stay together really well. Like in that lattice structure we saw earlier. It's not like that where they stay together really well. These bonds are incredibly weak, right? I mean, if you have a bottle of water next to you, just shake it around, right? And you just by doing that, you broke apart millions and even probably billions of hydrogen bonds just by shaking around your water bottle, right? Because these are constantly moving, they're constantly shifting around. It just takes a little bit. It just takes a little bit of force to get these apart, right? And we'll get into later as to why that's super duper important in biological systems, right? Because if everything was covalently bonded in our bodies, right, really bad things would happen because, well, for one, you wouldn't be able to breathe, right? What if your cells were just locked in one position for its entire lifetime, right? Hydrogen bonds are incredibly important. That's why water has surface tension, right? That's why certain bugs can walk on water. They take advantage of these properties of water that you're able to do because of hydrogen bonding. Hydrogen bonding creates like here's an example, right? In action movies specifically, you often have like a guy jumping out of a helicopter or falling into water. From a certain height, water acts like concrete, right? I don't know if you guys have ever went into the swimming pool and belly flopped into the pool, right? It's painful. That quick like slap of your body and the water is because of hydrogen bonds, right? These hydrogen bonds like to stay together. They keep water together. That's why water takes forever to boil, right? It's because we're breaking apart these hydrogen bonds. It's an incredible thing. Hydrogen bonds are super duper important, right? And it only happens between it can only happen between molecules that are polar, right? So water is a polar molecule, right? Because it has polar covalent bonds. Because oxygen is sharing those electrons unequally, right? So, with that in mind, right? With the properties of water in mind, and with polar covalent bonds in mind, and with non-polar covalent bonds in mind, right? Just take that all into consideration. So this is a property that's present in water, the ability to hydrogen bond. That's not present here because remember, molecules that share equally are non-polar. They are non-polar. Molecules that share equally are non-polar. Molecules that share unequally are polar, right? And like I said, that all has to do with electronegativity. So, one big takeaway, one thing that you're probably most interested in learning, one thing that you have to remember is what bonds are polar and what bonds are non-polar covalent, right? So I'll tell you. Carbon bonded, okay, well, for one, anything bonded to itself, non-polar, right? The electronegativities just cancel each other out. They share equally. Perfect, right? So that's oxygen bonded to oxygen, nonpolar. Hydrogen bonded to hydrogen, nonpolar. Carbon bonded to carbon, nonpolar. Anything bonded to itself, nonpolar. That's what I'm trying to say here. So oxygen gas, O2, that's what we breathe in, right? That's in the air. This is a double bond I'm going to draw, which we don't need to know about double bonds quite yet. That's basically what it is. Nonpolar, right? Despite the fact that oxygen is such an electron hog, it's still nonpolar because it's still bonded to itself, just like hydrogen over here, right? So anything bonded to itself is going to be nonpolar. Let's write that down. Anything bonded to itself is nonpolar. Good. Good. So now we know that. So how about everything else, right? Well, there's only a few bonds that you need to know their properties, right? And they are carbon bonded to hydrogen is nonpolar. Carbon bonded to oxygen is polar. Carbon bonded to nitrogen is polar. Oxygen bonded to hydrogen, as we learned, is polar. Yeah, I think I'm missing one. Oh yeah, and nitrogen bonded to hydrogen is polar. So all of these you have to know, right? You have to know for the future. Maybe not necessarily for this exam, even though it will be certainly helpful, especially in the case of hydrogen and oxygen. And in fact, no. Hydrogen and oxygen and carbon and hydrogen are the ones that you definitely need to know for this exam. But in the future, these are all the ones that you need to know. Most of them are polar, right? Because nitrogen is a bit of an electric hog, just like oxygen, right? But what about carbon and hydrogen, right? These share almost equally. Carbon has like a medium electronegativity. Hydrogen has a medium electronegativity as well, right? So good, yeah. So we learned all about bonds, right? How wonderful is that, right? We learned all about bonds. This is the foundation for what we're going to learn throughout the rest of the semester, right? So let's look at this. Right, so let's look at this this periodic table. So we're gonna ignore hydrogen for now. Elements on this side, on the left-hand side, elements on this side are going to want to form ionic bonds. Because they're just dying to get rid of those electrons, right? Elements in this column specifically have 2 electrons that they want to get rid of. Elements in this column have 1. So if you ever see anything about sodium, potassium, lithium, they have 1. And for 2, if you ever see anything about strontium, probably not, calcium and magnesium, it's going to have 2. Which the question will let you know if how many electrons it has, or its atomic number, which you could assume the valence electrons, that sort of thing. And elements on this side are going to want to covalent bond. These are going to want a covalent bond, right? With a few exceptions, right? We learned about sodium chloride, right? So these are going to want to just fill out that one last electron, right? That one last electron in its shell. That's what fluorine, chlorine, and bromine want to do, and iodine. But they're a little bit different, right? Solely because they are still able to form covalent bonds with each other. For example, fluorine can form a covalent bond with itself, and chlorine, and bromine, and iodine. All of these can form bonds with themselves, right? Which these are all what are known as halogens, right? I love halogens. Halogens are so cool. Anyway, just as a general tendency, these want a covalent bond, with the exception being these ones, which they can ionic bond, but they could also covalent bond. Except for, but in the case of these are almost always going to be ionic bonding, right? So if you ever see sodium and chlorine, or magnesium and chlorine, or potassium and bromine, it's most likely gonna be an ionic bond. Everything else most likely going to be a covalent bond. And remember, right? We learned about the 5 bonds that we need to know their properties of, the polar covalent versus the non-polar covalent. These are these ones, right? These ones. So yeah. Anyway, we're about an hour and 10 minutes in, and we're not very far through the actual exam, which is hilarious, right? So we've learned pretty much everything that we need to know for the rest of the exam. We've learned almost everything, and if there's something that hasn't come up, we're going to talk about it. So, with that being said, we are going to speed run through the rest of the practice exam. Let's do it, yeah? So, let me find the next question. 6, right? It's been an hour we've answered 5 questions. Can you believe that? It's all my fault, right? I spend a lot of time explaining things, which I hope is helpful for you guys. Yeah, anyway. Number 6, a molecule with polar covalent bonds. We just learned about this, right? We just learned about this. A molecule with polar covalent bonds will be soluble in water, not soluble in water, contain atoms with very similar electronegativities, or B and C are correct. Okay. So anything with polar covalent bonds. What is a polar covalent bond again? Right. So one thing I should say is that water is not the only molecule that is able to make hydrogen bonds. Anything with an OH or an NH or an OC or a CO, whatever, all of those have the potential to make hydrogen bonds. Right? That's why sugar is dissolvable in water. That's why you could dissolve sugar in water, because sugar has tons of OHs, right? But sugar isn't water, right? But it can still dissolve in water. It's still soluble in water, meaning being able to be mixed in water. Well, how about oil? Oil is almost entirely made of CHs, and CHs are nonpolar, right? So another big principle that we need to know, another big principle, is that like dissolves like. Like dissolves like. That is a huge, huge principle, right? So if you have something that's oily, it's going to want to dissolve in something else that's oily. Oil and water do not mix because they are not alike each other. Something that's able to be dissolved in water is going to want to mix with water, like dissolves like, but it's not going to want to be able to dissolve in oil, right? Have you ever tried mixing sugar and oil? I mean, I'm not really sure what would happen, but I don't think it would mix nearly as well as it does with water, right? Because they're not similar to each other. So, a molecule with a polar covalent bond, meaning that it is able to make hydrogen bonds, it's able to mix with water because they're both polar, they're both able to have that interaction with each other, right? Because one's positive, one's negative, right? They're both able to make that interaction. That would be soluble in water. So that's the answer, A. Would be soluble in water. So B and C are not correct, right? Because what is B? Not soluble. And what is C? Atoms with very similar electronegativities. So what did we just say about oxygen being an electron hug, right? Oxygen has a very high electronegativity. Oxygen loves to pull the electrons from hydrogen. So a molecule with polar covalent bonds would in fact not have very similar electronegativities. In fact, they would be quite different. Moving on. So we were just talking about this, right? We're just Just talking about this. Hydrogen bonds are formed between any molecules that contain hydrogen, which, not true. We just talked about hydrogen gas, which is nonpolar, right, because it's hydrogen bond to itself. So any molecule that contains hydrogen will not necessarily form a hydrogen bond. B, only between water molecules. Once again, not true, because sugar can form hydrogen bonds, right? That's why sugar is able to be dissolved in water, right? It has the ability. It has that polar quality about it, right? C, when hydrogen is part of a polar bond, okay, now we're getting somewhere. And then when two atoms of hydrogen share an electron, not true. Once again, we just talked about hydrogen gas. So when hydrogen is part of a polar bond, what is that? Right? That's O and H, and that's N and H. Right? So hydrogen with that partial positive charge is able to seek out other negative charges around itself, right? So that partial positive charge is able to seek out the negative charges, and the negative charges on oxygen are able to seek out positive charges. Bam. C is the answer. So, oh, sorry if I keep blinding you by turning the screen white all of a sudden. Okay, so once again, we just talked about this. Guys, there's not a whole lot that you need to know for this exam. I know it can seem very daunting, essentially joining a chemistry class, right? Because this first like quarter of the class is mostly chemistry. But guys, there's not a whole lot like that you need to like remember. Right? You just have to understand how each of these concepts relate to each other and how to reconcile with that, right? Because we've talked about nearly everything, and everything is just kind of coming up now, right? So what A is asking, if you shake a bottle of oil and water and let it sit, it'll separate into two phases because one is polar and one is nonpolar. So what does that tell us? A, the nonpolar oil. Oh wait, sorry, I should have read that. Bam. D, the nonpolar oil is not soluble in water because remember, water is a polar solvent. Oil is not. Like dissolves like, and these are not alike each other. So D would be the answer, right? And water cannot form hydrogen bonds with the oil because oil is primarily C and H, right? So yeah. If you answered B, just think. sorry, I gotta cool down a little bit. So if you answered B, just think about it, right? If you shake a bottle of water and if you mix oil and water, it says in the question it will separate, right? So water can form hydrogen bonds with itself, right? But water doesn't separate from itself. That would be silly, right? So if water can form hydrogen bonds with oil, wouldn't it make sense if it actually could? If it actually couldn't separate? Right? Even if you didn't know necessarily. Anyway. Right, if you answered C, right, polar oil is not soluble in water. Well, like I said, like dissolves like, right? So water is polar. If oil were polar, then it wouldn't have separated into two phases. This is like B with extra steps, right? or C or B is C with extra steps. Anyway, if oil were polar, it would not have separated, right? It would be soluble in water. So yeah. Anyway, let's move on. Okay. So number 9 is asking. Whoops. Sorry, give me 1 second. Number 9 is asking the mass number of an atom is 15 and its atomic number is 7. The atom probably has 7 electrons in the nucleus, at least 15 electrons, about as much mass in electrons as in protons, 7 units of negative charge in the nucleus, 8 neutrons in the nucleus. So let's look at this, right? 7 electrons in the nucleus. Are electrons present in the nucleus? No. A is out, right? 7 units of negative charge in the nucleus. Okay, well, what has negative charge? Electrons. What has positive charge? Protons. What is in the nucleus? Protons. D is out. About as much mass in electrons as in protons. Well, do you remember what we said earlier about an electron containing 1% of the mass of a proton? Again, that one's out. So what's left is at least 15 electrons and 8 neutrons. So what is it? So atomic number, remember, that represents the number of protons. That's what atomic number is. Now the mass number tells us how heavy the atom is, right? How many neutrons it has, how many protons plus neutrons it has. So from this we can calculate 15 minus 7 gives us 8, right? So what does it leave us with? E is the correct answer. But what about B, right? What about B? At least it's 15 electrons. So there wouldn't be at least 15 electrons. There would be at least 7, right? Because the atomic number is 7. That is the amount of protons. And for that to be equal, for them to be equal, for it to be stable, for it to have the same amount of positive as it does negative, it would need 7 electrons, not 15, because 15 is the number of mass. So this would be so at least 15 electrons would be the amount of protons plus neutrons, which is not the case. So yeah, moving on. Okay, number 10. Two atoms always represent the same element if they have the same number of shells, electrons, particles in the nucleus, same mass number, or same protons. Okay. So do you remember what we said earlier? All the way back like an hour ago at this point. How the different particles have their own different thing going on. Electrons changes it has to do with the reactivity of the atom. Neutrons, stability. Protons, it changes the atom itself. It's the property of the atom, right? So mass number can change the number of neutrons, right? Number of particles in the nucleus can change, that's also neutrons. Number of electrons can change, that's ions. Number of shells, electron shells can change because if you get rid of one or if you add another one, all of those can change. They can still be the same element. However, what never changes is the number of protons, because otherwise you change the element. So that would be D. Moving on, we have number 11. So number 11 is saying, oh, dang it, okay. Number 11 is saying covalent bonds hold atoms together because they, A, allow atoms to fill the valence shell, so we could just ignore that one, right? We don't allow atoms to fill a valence shell, we allow electrons to fill a valence shell, right? B, bring electrons closer to protons. Not true, right? Electrons like to stay in their shells, right? They don't like to go to the nucleus. C, rely on electrostatic attraction. Okay, that more so describes ionic bonds. That describes ionic bonds, right? So we can go ahead and eliminate C. Where D, atoms are always more stable when they share electrons. Bam, that's our answer. Just the fact by share electrons, that's covalent bonding, right? Which is also true. You know, they are more stable than they would be with the other things that they describe. I mean, covalent bonds are, of course, the most stable bond that there is. Okay, so let's move on to number 12. And, oh, dang, we're not even halfway done. Oh my goodness. Please bear with me. This is a little bit lengthy. Yes. So we're just gonna go ahead and go through the rest of it because that's what I'm here for, right? We are now we're in 25 minutes in. Yes, sir. We are. Like I said, I said I would go through these quicker, but some of these still require the explanation that they need, right? So number 12, when an atom of oxygen, sorry, I had to crack my back. When an atom of oxygen makes a covalent bond, why does the atom's charge stay close to zero? Okay, so this is a question that's not going to be expected of you. Um, Basically, what this question is saying, right? So I'm just gonna tell you the answer. It's B, right? The answer is B. But why the atom's charge is when an atom of oxygen does make covalent bonds, the valence shell no longer has 6 electrons. We can eliminate that. The atom loses electrons from the shell. Also not true. And the charge isn't 0. It's -2. Not true. Right. So why is B the correct answer? Shared electrons aren't always near oxygen. Well, do you remember how I said that oxygen is a bit of an electron hog? Well, that's only for most of the time, right? Because sometimes, maybe, an electron will be closer to hydrogen, right? Or maybe it'll be further away from oxygen. Maybe it could be basically anywhere, right? Because electrons are very finicky. They are very fast. They're very quick. They kind of do what they want. That's an electron, right? So shared electrons aren't always near oxygen because sometimes that shared electron is going to be near hydrogen, right? And sometimes that shared electron is going to be near the other hydrogen, right? Or maybe it's going to be near carbon or whatever, right? So the atom's charge stays close to 0 because, well, yeah. But this question, like I said, is most likely not going to be expected of you because that's a very like chemistry question. That was from like 21. That was from like 2110, which is a few years ago at this point. It's number 13. So, which answer helps to explain why carbon atoms tend to make 4 covalent bonds? Well, okay, well the first electron shell needs 4 electrons. That's not really true, because it's not the first. It's not the first shell. It's the valence shell, which is the second shell, right? The carbon nucleus has 4 protons, which is not true. It has 6, right? The valence shell initially only has 4 electrons. This is true, so we could say that's correct. The carbon will form an ion by losing 4 electrons. Super duper unlikely, if not impossible. No. And none of the above. Carbon makes 3 covalent bonds. Not true. It can make 4. So the answer is C, right? So carbon can make 4 covalent bonds. Simple as that, right? A valence shell initially only has 4 electrons, so that means it has 4 spots that are able to be filled. Right, so we have carbon, right? So this is the valence shell. We have 1, 2, 3, 4 unpaired electrons. We could share 4 bonds, just like that, right? Okay, moving on. Dang, I did it again. Okay. Okay, an anion with a charge of -2 has 8 protons. The ion also has what? Okay, so 8 protons. 8 protons. So when this wasn't an anion is just an anion. Excuse me. Sorry. An ion is just an ion with a negative charge, and a cation is an ion with a positive charge, right? So that's a negative charge, right? So initially, 8 protons. This at one point had 8 electrons. So with a charge of -2, that means we added 2 electrons. So when we add these together, we get 10, right? So that's our answer, 10 electrons. So anion, I think, is a word that you need to understand for the exam, and cation is also another word that you need to understand. Like I said, there are just 2 types of ions. One's positive, one's negative. Cation is positive, anion is negative. So yeah, moving on. And speaking of cat ions, my cat has decided to make a guest appearance. So if you hear him meowing or causing general mayhem, he is here with me. So number 15 has an image attached to it, so I'm going to try and put that here now. There we go. So number 15 is asking, the atoms shown here will become ions if they meet because A nearly full shell has little attraction for electrons. Okay. B, atoms tend to have filled valence shells or will take or donate electrons to fill the outer shell. Okay, that one's true, right? Or C, a nearly empty shell attracts electrons very strongly. Okay, so if you switched up A and C, if you switched up their definitions, they would actually be correct, and therefore D would be correct. But they're not. So a nearly empty shell attracts electrons very strongly. Not true. It is very much. And now that I'm thinking about it, these definitions don't even really make much sense. Attracts electrons very strongly. A nearly empty shell attracts electrons. No. What would happen is an empty shell would want to get rid of the electron as much as they possibly can. If anything, a nearly empty shell would have a little attraction. So what about nearly full? Nearly full would have a very high affinity for electrons because it wants to fill that shell, right? So B would be the incorrect answer. Sorry, D would be the incorrect answer, leaving B as our only option. Atoms tend to have filled valence shells and will take or donate electrons to fill the outer shell. So let's just see what's going on here. We have one. So we'll just see what would happen to these two, right? These would probably become ions because this one just wants to donate its 1, and this one wants to accept the 1, right? So bam, it's going to give that electron there, and it's going to get rid of this one. So that's why they would form ions. And like I said, atoms tend to have filled valence shell when they want to take or donate electrons to fill it, right? Like that's how they would fill it. Anyway, sorry. Oh my gosh, this is exhausting. I think I need a glass of water or something. Anyway, yeah, I'm gonna hopefully try and keep this under 2 hours because I know it's late at this point. At this point in time of posting, it is quite late, and I apologize for that. I've been quite busy the past few days, and I really want to get this video out sooner, but I had a lot of technical difficulties as well. Anyway, so number 16 has another image associated with it. Whoops. So each carbon atom in this molecule is forming 4 covalent bonds. Okay, so this right here is a double bond, which is essentially 2 covalent bonds, right? Just back to back, right? It's where we take 2 unpaired electrons and we just pair both of them to the same element, right? So in this case, oxygen has 2 unpaired electrons that are both bonding to carbon. However, so they count for 2, right? Double bond makes sense, right? So this question is asking to focus on the carbons, right? So this carbon atom has 4. Okay. This one has 4. Okay, this one has 5. Right? So we have 1, 2, 3, 4, 5. So that makes this false. Okay, so once again, we just talked about this. Right? We just now talked about this. No need, don't even stress. We just discussed this one, right? Within a water molecule, within a water molecule, the atoms are held together by blank bonds, and two water molecules are held together by each other by blank bonds, right? So remember, inter versus intra molecular forces, between versus within, right? So within a water molecule, these atoms are held together by what? Polar covalent or non-polar covalent? Well, O and H, H2O. O and H is one of the few bonds that I told you to remember, right? And what are they? Polar covalent, right? So we can just go ahead and eliminate A, D, and B, right? And C for that matter. And two water molecules are held together to each other via hydrogen bonding. Because remember, H bonding is intermolecular force. It happens between two molecules. Okay, moving on to 18. Okay, fluorine or fluorine. Fluorine has an atomic number of 9. How many electrons are needed to complete the valence shell of a fluorine atom? Well, 9 minus 2 equals 7. So we need one more. So that's going to be A. 9, we don't need 9 electrons because it already has 9 electrons, right? 7, I don't know where 7 came from. It has 7 valence electrons, sure. Other than that, it needs one more to fill it out. 0, well, fluorine is not a noble gas. It still has the one electron that it needs to pair. Yeah. And 3, I don't even know where 3 came from. This is just the most wrong. 1. It needs 1 electron. Because remember, if it's under 10, it's the number minus 2. It's over 10, it's the number minus 8. Sorry, if it's under 18, it's the number minus 8 minus 2. If it's yeah, we won't get anything over 20, right? So in this case, 9, right? So that's 9 minus 2, 7, right? Because we have the inner shell. So atomic number of 9, 9 protons, 9 electrons, minus 9 minus 2, 7, 7 valence electrons. We need one more to fill the shell, right? Something like sodium has 11, right? 11 minus 8 minus 2 equals 1. It needs to get rid of 1 to fill the valence shell. Oh, this one's a long one. All right. A covalent chemical bond is one in which electrons are removed from the atom and transferred to another so they become oppositely charged. Well, that sounds a lot like ionic to me, so we just go ahead and cross that one out. B, protons and neutrons are shared by two atoms to satisfy the requirements of both atoms. So keyword is neutrons here. They don't share neutrons. Neutrons stay unopposed. Outer shell electrons of two atoms are shared to fill the electron shells of both atoms. That one's the most correct so far. Outer shells of one atom are transferred to fill. Transferred, right? So that sounds like exchange, right? Again, ionic bonding. Not the case. And E, an electron occupies a hybrid orbital located between the nuclei of two atoms. What the heck does it even mean? I mean, honestly, what the heck does it even mean? I mean, did we learn that at any point? No, we did not. That one's wrong. And so the answer is C. They are shared. They share electrons between two atoms. We learned that, correct? Yes, we did. All right, next question. Okay, so number 20 is saying, what is the maximum number of covalent bonds with an element, or sorry, what is the maximum number of covalent bonds and element with the atomic number of 8 can be with hydrogen? So if you know what the atomic number, if you know what the element with the atomic number of 8 is, it's super easy. But let's assume that we don't, right? So remember, 10, if it's under 10, right, you just subtract 2, right? So what's 10 minus 2, right? That's, where did I get 10 from? Sorry, what's 8 minus 2? That's 6, right? So 6 valence electrons. So that means, so if we take 8 minus 6, then that means there are 2 bonds that are able to be formed. 2 bonds are able to be formed, right? So how many covalent bonds? What's the max number of covalent bonds in an element with atomic number of 8 can be with hydrogen? Well, the answer is 2. So that's our answer, 2. Okay, so this next one is going to require a little bit of explanation. Where's C? Oh, we're missing one. Oh, well, actually there is no C. Sorry. Dang it. Okay. There we go. Okay, so this question is asking, when salt is dissolved in water, which bond described below is not broken? Well, the answer is this one. That one's not broken. These other 2 are broken. But that's not satisfying enough. So what's going on here? So what is salt? What is table salt? NaCl. We discussed that earlier, right? How these are both ions, right? And they like to stick together via an ionic bond. But what is water? Well, water is H2O, right? And what does water have? Polar covalent bonds. What are polar covalent bonds able to do? Hydrogen bond. Right? So these have partial positive charge. The hydrogens do. And then the oxygens have partial negative. Right? So what's essentially going to happen is that the water is going to pull apart the salt. Right? I mean, I'm sure you guys know how easy it is to dissolve salt in water. Right? It just like happens like that, right? Very simple, right? And that's because of this. That's because of these partial charges, right? This positive charge on the hydrogen is literally pulling. It's pulling itself towards the negative charge in the chlorine, right? And similarly, the positive charge in the sodium is pulling itself towards the negative charge in oxygen, right? So then these get pulled apart, right? So now we have sodium ions in solution. And we have chloride ions in solution, right? Which you don't need to know necessarily what that means, but just know that in this process, an ionic bond is broken, and a hydrogen bond is also broken because we had to break apart hydrogen bonds to do this, right? We had to do it because hydrogen bonds are constantly being broken anyway. But in order to do this, sodium is attracting those waters to itself. And chlorine is attracting, again, the waters to itself. So it's in that sense, it has to break those hydrogen bonds, right? So water is literally, it's literally breaking apart salt, right, in this process. And what water can do is it could literally like surround itself, right? So it's just like shoot, sorry. There we go. And if I could rotate this, I would. This I could probably try and let's see. Yeah, there we go. Okay. Yeah, that's close enough. So yeah, this is for sodium, right? All of the negative oxygens are it's attracted to the sodium, right? And over here, um, it would be for the hydrogens, right? Just like that, right? These waters just love to be near the salt because just because of how attracted they are to them, right? So that's number 21. So let's see how we're doing on time. About an hour and 46 in. We're probably gonna get done with this before the 2 hour mark, which again I know it's late. I really apologize. I could talk fast sometimes, but if you really need to, you could watch this video and excuse me, 2 times speed. Anyway, so number 22 is asking which term refers to substances that are not easily dissolved in water. Okay. If you guys looked at my terms, my Greek and Latin prefixes and suffixes, you would know what philic, phobic, and hydro mean, right? So what are these? So if you didn't look at it, I encourage that you do. But in case you didn't, hydro means water, phobic means fear of, and philic means affinity for or liking of. So, what term refers to substances that are not easily dissolved in water? Well, all of these are easily dissolved in water, right? Something that's hydrophilic. Remember, like dissolves like. For ionized, well, ionized are charged, right? When we saw just how much water likes ions, right? They like the charges, right? Polar, water is already polar. Remember, like dissolves like. So the term here would be hydrophobic. So something like fat would be hydrophobic. Something like oil would be hydrophobic. Something like a steroid would be hydrophobic. And that's going to be super, super helpful later on. So number 23. Which of the type of covalent bond represents a non-polar covalent bond? Do you remember what we talked about earlier? What did I say? What were the 5 that you need to know? O and H, C and H, C and O, C and N and H. Well, which one here is the only non-polar covalent bond that we talked about? It's going to be B. O and H, super covalent. C and O, sorry, O and H, super polar. C and O, again, polar. So yeah, moving on. The next one is like a matching. So we're gonna take a little screenshot. So which type of covalent? Oh wait, sorry. It's gonna mess up. Oh, never mind. Okay, what were we saying? Okay, so match the terms with the correct definitions. Number 24 describes a substance that cannot be broken down into any simpler substance. That sounds to me like a neutron. Just kidding. It's an element. It's an element. That is an element. So we got that one down. Number 25. The weakest type of interaction found between molecules in cells. That would be a van der Waals force. Which, before we go, I will discuss van der Waals forces. So number 26, the subatomic particle that does not contribute to an atomic atom's weight. Well, neutrons definitely do. And ionic bond does not apply here. So the answer is E, electron. So, what in the heck are van der Waals forces? Van der Waals forces are interactions between molecules that are so weak that they barely even count, but are ultimately very important. I like the example of methane, right? Methane and octane. So methane, so okay, for starters, okay, there we go. There was like a disconnect that happened for a second there. Sorry about that. Where was I? So yeah, consider how weak hydrogen bonds already are technically, and like make like a fraction of a percent of that. Van der Waals forces are very, very weak. So what essentially a van der Waals force is that it just describes like that in a fraction of a second, literal like nanosecond, or even in some cases femtosecond, like such a short, inconceivable amount of time, there would be like a slight negative charge here. Oh, excuse me, sorry. There would be a slight negative charge here in the hydrogen, and a slight positive charge here in the carbon, and then it goes away. Fraction of a second, right? Super, super short. So this very, very slight electrostatic interaction attracts these methane molecules for like a split second, and they split apart, right? For a split second, and then they go away, right? Because methane is a gas, right? Methane is what cows burp out. It's natural gas. You could burn it, that sort of thing. That's what methane is, right? Now there's the other example of octane. So octane. So octane has 8 carbons in its chain. And with each carbon is a hydrogen. Oh man, this is gonna take forever. Sorry. So essentially, octane. Okay, so what is octane for one? Octane is the stuff they put in race cars to make it go faster, right? It's fuel essentially. It's really efficient fuel. So octane is literally like 8 times the size of methane is, right? So if we take another octane molecule, if we take another one of these, and they interact with each other, sorry, my cat just appeared out of nowhere. If these molecules interact with each other, it's going to be a much larger interaction than methane was. So that's why octane is liquid at room temperature, and methane is gas at room temperature, right? Just because it has more chances for those van der Waals forces, just for that very slight, very instant electrostatic attraction that happens between the two molecules, right? Like I said, very, very small interaction, but that's why one is liquid, one is gas. Anyway, it only happens between nonpolar molecules. Well, maybe not only. It happens when we think of van der Waals interactions. Think nonpolar interactions. So yeah, it happens almost exclusively nonpolar interactions. So anyway, at the time of finishing this, it is 10:30 at night, and and the Wi-Fi went out again. Okay. Oh, there it is, back again. Okay. This video has run along for almost 2 hours at this point. So my advice to you all is to just take what you need, right? If you have trouble with bonds, I had an entire section on bonds. If you're having trouble with subatomic particles, I have an entire that was at the beginning of the video, right? Everything that you need to know for the exam is here, with the exception of like some of the like domain stuff, some of the animal kingdom stuff. Everything else that you need to know, everything about the atom that you need to know is here. So, in any case, I hope you guys enjoyed the video. It was very long, but I really hope that it was helpful and that this is going to be a resource for you. So yeah, in any case, I hope you guys have a good day. Take care, or good night rather.